Force, work, and energy review 6. From the graph, find the work done on the mass between x equals 0 meters and x equals 6 meters. We have force with displacement, and there's our mass right there, 8 kilograms. The work done is going to be the area, isn't it, under the graph. So let's do that. I'm going to break this into two parts. I'm going to break it into a trapezoid right there, and then I'm going to break it into a triangle right there. So let's see if we can do that. The area of a trapezoid is 1/2 times the sum of the parallel sides, which is 20 on that side and 40 on that side, and then we multiply by the width, which is 3. So I think that's the area of the left portion of that graph, and then here we have a triangle, so that's going to be 1/2 times 3 times the height, which is 40. All right, what does this come out to be? 60 divided by 2 is 30 times 3, so that's 90, and that's going to be 60. So I'm thinking 150. 150 joules worth of work was done on this mass. That mass of part 1 has an initial speed of 4 meters per second. So initially, that's how fast it's going. How fast is it going when it is at the location x equals 6 meters? Well, the fundamental idea of physics that we want to invoke here is the net work done is equal to the change in kinetic energy. We decided that the net work done was 150. We just found that out. And the change in kinetic energy is 1/2 times the mass times the quantity V final squared minus V initial squared, which looks like that. So 4 squared is 16. So what does this come out to be? We might have to use a calculator for that. So that's 300 divided by 8 plus 16. I think if you put that into your calculator, I did a little while ago, and I got a VF to be 7.3 meters per second. You check and make sure that that's right. Here we've got a force and a displacement, and we want to know the work done. The work is the dot product of the force and the displacement. And we said that if you have vectors in unit vector form, you multiply the I-hats, and that's going to be -2 times -5, and then you multiply the j-hats, which is 5 times -2, and then you multiply the k-hats, which is -1 times 3. Check and make sure I didn't make a mistake there. That looks good. So that's +10, that's -10, so that's going to come out to be -3. -3 joules. And we do want to report that as -3. Is the angle between the vectors acute or obtuse? Now, we need to know what acute and obtuse mean. Acute means that the angle between the vectors is less than 90, maybe, something like that. Obtuse would mean that the angle between the vectors is more than 90, maybe, something like that. We know that this angle is going to be an obtuse angle. And the reason it's obtuse is because negative work was done. And the only way that negative work can be done is if, let's say this is the force vector here, its component of the force that is parallel to the displacement points in the opposite direction. So this must be an obtuse angle. It might not be a very big angle beyond 90 because that's a pretty small number of joules there. Well, we want to just use the Pythagorean theorem on these. The three-dimensional version of the Pythagorean theorem. Basically, we're going to square, can I get that on there? Yep, can you see that at the top? We're going to square 2, which gives us 4. We're going to square 5, gives us 25. And then we square 1, which gives us 1. So it's essentially the Pythagorean theorem. And if you turn this into a decimal, this is going to be the square root of 30. So it's going to be something over 5. And my calculator tells me that it is 5.48 newtons. So that's the magnitude of that vector. And then we do something similar for S. We're going to square its I hat component, which is 25. We're going to square its J hat component, which is before, and we'll square its K hat component, which is 9. So that's going to be the square root of what? 38. Square root of 38, which should be a hair more than 6. And my calculator says 6.16 meters. So that's how you determine the magnitude of any vector. You just take its components and Pythagorize them. Now, what's the angle between these vectors? The dot product is found by taking the magnitude of each of those vectors and then the cosine of theta. We know that the dot product came out to be 3, -3 actually. That was the first thing we decided. Let me scoot up here so you can see it. There it is, right there, -3. So that's the dot product, which is the work done. You can see there's the work done when we took the dot product. So -3 is the left side. We just found the magnitudes of both of these. The force had a magnitude of 5.48, and the displacement had a magnitude of 6.16. And then we have the cosine of theta there. So we'll definitely need a calculator for this, and we have to use our inverse cosine function right there at the end, don't we? Well, when I did that, I got theta to be 95 degrees. Sure enough, it is an obtuse angle, and as we predicted a little bit ago, it's not real obtuse, just a hair beyond 90. And we guessed that it might be that way because of the low magnitude of this negative work right there. So I think that's how you do that.